Okay. After this theoretical high redshift talk, we now change topic completely, and we go over to Dr. Arpita Roy, who did her undergrad at the Franklin and Marshall College in Manchester, with actually an honors major in astrophysics, but also a major in creative writing in 2009. She then continued to do her PhD at Penn State and won several prizes for her PhD thesis, including the Distinguished Doctoral Scholar Medal by Penn State or the University Dissertation Award, but also an award called Dr. Doxy Dissertation Award by the AAS. And I'm very excited that now she's this Robert A. Wilkerson Prize postdoctoral fellow since 2017 and will tell us about instrumentation. So thank you.
Thanks. Yeah, I'm excited to be here. I've actually been collaborating with scientists at UT and building instruments for McDonald for a while, but I've actually never been on campus, so this is cool. So I'm going to tell you about radial velocity exoplanet detection and where the field is going, show you some early results, and then discuss a little bit about the other science we get when we build these very awesome spectrographs that are highly stable. So I'm going to start with this very cute little animation of the history of exoplanet detection. So we're going to start in the 1700s and go to about present day. So for a while, nothing really happens. There's 6 planets in the solar system. Then we find a couple more. And then soon Pluto is discovered and is a planet for a while on this animation. And then in the 90s, you see the first radial velocity planets coming up, a few transiting planets from the ground, and then soon you'll see Kepler and the effect of Kepler, which was to sort of overwhelm our understanding of the demographics of exoplanets. It's a little hard to read the legend here, but these are the different detection techniques. And of course, transits with Kepler sort of overwhelms everything, but radial velocity is plugging along on the ground. And there's a few other methods with a handful of planets, some of which will get magnified as Gaia data gets processed over the years. And so in this context, I work on the radial velocity detection of exoplanets. And so, of course, that means we're watching the effect of the planet on the star. So the star is wobbling in response to the gravitational pull of the planet. And the spectrum of the star is slowly being red-shifted and blue-shifted as the planet orbits the star. This is the basics of radial velocity. But the sort of place we're in now is that we're digging into smaller and smaller signals to try and find the signatures of smaller and smaller planets on these stars. And so the real world analogy I like to give is that of a desert tortoise. So we're trying to get to about 10 centimeters per second precision. That's slower than you walk. It's about the speed of a tortoise. That's how much the star is moving. That's how fast the star is moving. And it's light years away. So it's kind of mind-blowing, the scale that we're trying to measure here. So that's the animal example, and here's the physics example. So this is an image of the silicon lattice of, say, a CCD. And on this scale, the movement that we're trying to measure is about 10 centimeters here, which if you count is 1, 2, 3, 4, 5 silicon atoms apart. And so even in a real physical sense, we're making a very, very difficult measurement and coming up against some fundamental physics barriers here. But we are trying to do this because 10 centimeters per second is the signature of the Earth on the Sun, approximately. And so if we really want to find habitable zone planets that are rocky like the Earth, around stars like the Sun, we have to be able to do this. And so to try and do this, the field of radial velocity has sort of been energized in this era of tests. And in response to the last decadal, which said ground-based radial velocity should be supported, 23 new instruments are coming online now. So starting in about 2016, going up to 2023, there's a lot of observing power with precision RVs coming online. And what I've shown you here also is some of the spacecrafts that are launching along this timeline that will provide a lot of the targets that will be followed up with these ground-based instruments. So I'm involved with quite a few of these. So 6 of these instruments that I'm working with now. Some take up more time than others. But these are all sort of bringing to the fore different capabilities. Obviously, to convince your funding sources, you need to be special in some way. And so each of these 6 instruments that I'm working on has their own highlights. So NUID is an instrument that I'm going to talk about a little bit more. This is a Penn State instrument that is going on Kitt Peak on the 3.5 WIN telescope. And it is possibly our best bet in terms of US access of getting to 10 centimeters per second. This one might look familiar to some people in the room. The Habitable Zone Planet Finder is at the Hobby-Eberly telescope at Texas. This is a near-infrared spectrograph, and so it's going after planets, small planets around redder stars. An instrument that I worked on actually before I started grad school, Paras, now has a progenitor, Paras 2. This is on a small telescope, but the nice thing is this is in India, so it's just about 12 hours away from the continental US telescope, so it provides really nice coverage longitudinally. An instrument I work on at Caltech that I'm project scientist for is the Keck Planet Finder. So this is scheduled for 2021. And it's going to combine a very stable platform with the 10-meter aperture of Keck, which is going to be very exciting. PARVI is an instrument that's being built at Palomar. This is behind adaptive optics, so it's part of a few instruments that are coming up that are really small because your beam becomes really small once you're behind AO. And so this is cheaper to build and easier to control thermally, for example, but these haven't quite been proven on sky yet in terms of precision. And another one that I'm helping out with is the SALT high-resolution spectrograph. So SALT is a twin of the HET in the southern hemisphere, and they have a high-resolution spectrograph. It's just never been commissioned to be full precision, even though it was built for it. So I'm helping them with that, but the southern skies don't have a lot of large apertures, so this is a cool one. Okay, so we're building all of these instruments, but how do we get them to 10 centimeters per second precision? So finding these Earth-like planets actually requires advances on many fronts. So lots of technical hardware fronts, but also software fronts, and scientific understanding as well. So understanding stellar physics better so that you can grapple with stellar jitter, which really will be the ultimate stopping block once the instruments get to be good enough. And so we're beyond the era of single dominant sources of error. So I get asked a lot, if you had enough money, what is the one thing you would work on or try to beat down? And unfortunately, there isn't a single one. You kind of have to get better at everything. And so what we've started doing is having a more systems engineering approach to building these instruments. And so we start by crafting what we call an error budget. And so this is basically thinking of every single term that could contribute to the error of your instrument and your precision, and tallying them all up. And you'll see there's different colors here. This is because NASA really likes color coding things. And so green here is things we understand, we have lab measurements of. Yellow is sort of educated guesstimates. Red are things that scare us, that we don't really understand. And some of these actually can't be measured except on the instrument itself. So to build the instrument to figure out what some of those red terms are. But another important thing to note about these error budgets is we don't say we have to get to 10 centimeters. How do we distribute this error? Instead, we build it bottom up. So we say, what are all the sources of error? What's the best we can do? And then where does that get us? Because it's a little hard to assign errors if you don't have the funding to back up that effort. So you'll see there's also different boxes here. That's because some errors are completely out of your control, and you just have to incur all of that error. But some things you can try to correct out as you're going along. And so you can try to beat down some of these boxes. So the basic philosophy of these next generation instruments is to actually put a lot of effort into the hardware. So these are not your run-of-the-mill spectrographs. These are built very, very carefully to try and minimize as many of those error sources that I showed you in the hardware, because it's much harder in the software. And so if you can eliminate some of those sources, you have a much better chance of getting to your goal precision. And so you do everything you can in the hardware, but then the software is your backup, and so you try and collect as many diagnostics as you can, so that then you can do it in the software. And the software, of course, is sort of future-facing as well. As we get better analytical techniques in the future, you can come back and actually make the data analysis better. So I worked on a few different parts of both the hardware and the software, so I'll show you some highlights, especially the stuff that works, that looks cool. And so we're going to step through a bunch of things that are stabilized to a higher level than ever before. So the first problem is getting your light from the telescope to the instrument. These instruments are all fiber fed, so they're usually really big instruments and weigh a couple of tons, and so you can't hang them off the back of the telescope. So these sit usually in the basements or some specially constructed room in the telescope that's pretty far away, and so you can't have free path propagation, and so you have fiber optics. But a feature of fiber optics is that they only allow the light to travel in certain modes inside the fiber. And so depending on the number of modes in your fiber, you get interference between those modes at the output. So here I'm showing sort of a worst case. So this is a Heaney laser going through a fiber. You'll see this is an octagonal fiber. This is what HPF and NUID has. And if you just put this very narrow wavelength of light through it, you get what we call speckle noise or modal noise. And you can imagine if you're trying to measure the centroid of this fiber really carefully to measure the movements in the star, it's going to be hard if there's all of this modal noise. And so there have been several versions of this, but we basically found that agitating the fiber smooths over all of this speckle noise. And so this started out when I was a grad student with me and Sam Halverson, another student, doing this, and then an engineer trying to build exactly that motion. And so this particular one is from KPF, which also adopts the design from HPF and NUID. But what happens when you do that is that you get this very nice smoothed beam. And so this is an animation as well, but you can see compared to the original, we really beat down modal noise a lot. This is especially a problem in the near infrared, and so this was sort of a high requirement for HPF. And once you meet it for the near infrared, you automatically meet it for the optical. Another thing I worked on was fiber scrambling. So this is the problem of trying to get your star into the fiber very stably, but your guiding isn't perfect and your star tends to wander on the face of your fiber. So this is a lab demo that I did to show sort of the worst case scenario where your star is moving now all the way across the fiber from one side to another. And you'll see this is the output of that fiber. And so while you can't exactly see what happened in the beginning, some memory of that input illumination change is still coming through. And if you take a PSF of that, which is like what the spectral line is, and where you will be trying to measure your movements at the 10 centimeter per second level, you'll see that the PSF changes so much underneath you that you would now not be able to tell if there was a planet around the star. It's changing at a few kilometers per second. And so this, again, can be a showstopper if you don't take care of it early in the hardware design. And there had been some designs for correcting this, but not at the level we needed for 10 centimeter per second precision. And so one of the things I did as a grad student was work on the use of these very small ball lenses. The idea of using ball lenses for fiber scrambling had been proposed before, but they'd never really worked. And the reason we got it to work is because Schott had just produced a new kind of glass that had a refractive index of exactly 2. And what happens when you have a refractive index of 2 is that if you put a little ball in the light of in the path of the beam, the ball focuses the light exactly onto the back surface of the ball, regardless of the size of the ball. And what that means is that you can butt couple the fibers and get really good scrambling. Also, butt couple is a real term. I feel like I get asked that. And so, not to belabor the actual design of this, but it literally is putting a little ball. So this one is for HPF, and it's a 2 millimeter ball that goes in between the fibers and is held in place very carefully. For NUID, this ball is 0.5 millimeter, so it's really tiny. And what it does now is scrambles the memory of this input illumination change such that the output is really, really stable. And again, this is an animation, but you actually can't see any variation by eye. So we were able to show like a 20,000 times level of suppression here, which sort of was the level that we needed. An interesting byproduct of this work was that we started thinking of other uses for this ball lens because we had a lot of extra lying around. And one thing Suvrat, my advisor, and I came up with is the fact that actually ball lenses are the oldest form of microscope. So back in the day, people would like melt glass and make beads and then look through it, and that was how you magnified things. Except this glass is really special, and so it's much better at magnifying things. And so we actually designed this biomedical device. It's a cell phone microscope, and so it's a really simple design, again, based on the ball lens. You clip it onto your cell phone, and it actually provides high enough resolution to resolve the nuclei of blood cells. So it's as good as a benchtop microscope in the lab. And this is Suvrat's blood. There's a really strict rule at Penn State that you can't require grad student blood for any projects. Makes me wonder why they needed to make that a rule, but it's cool because we were able to patent this design, and it was actually licensed by a company. So Penn State asked us if we wanted to form a company. We did not. We're astronomers. And so they found a guy who wanted to form a company, and he has, I think, the best CEO name I've ever heard. His name is Chase Millions. And so Million Concepts Inc. is now licensing this both as an educational device, because you can imagine doing really cool labs with kids in the classroom, but also as a diagnostic device in under-resourced areas. So you could do things like diagnose malaria or sickle cell anemia in the field really easily. Okay, moving on. So that was our fiber feed that we improved. Now we've gotten our light and our photons to the instrument itself. And so another thing we care about a lot is thermomechanical stability, because you can imagine if your bench is contracting a little bit or your optics are moving a little bit with respect to each other, this all affects your 10 centimeter per second precision. So both NUID and HPF are sort of in these armored tankers that keep them very, very stable. And you'll see here with respect to HARPS, which is sort of the current state of the art in radial velocity stability, NUID is a couple of orders of magnitude more stable in temperature and several orders of magnitude more stable in terms of pressure. And so all of this creates a very calm and stable environment. And then even outside this vacuum chamber, there's usually a room that keeps the variations between night and day sort of away from the instrument, and then the whole thing sits in the basement of the observatory. So that's the casing around your optics. Now we get to the optics itself. For all of these instruments, they're designed very carefully. They're sort of the underlying design is simple. These are all white pupil spectrographs. But the details of these designs are thought about really carefully. The spot sizes are made very small. For NUID, for example, they're extremely sub-pixel, which you might say doesn't really matter. Once you're smaller than a pixel, who cares how much smaller your spot is? But things like if the scrambling isn't great, then containing all of these things within a pixel actually helps. So this is the KPF optical design. An interesting thing about KPF is that the whole instrument is built of glass. So everything that is sort of this beige color is made of Zero-Dur, which is a very low coefficient of thermal expansion glass. So except for the camera barrels, everything else is made of Zero-Dur. So the bench is made of Zero-Dur, the optics are made of Zero-Dur, even the shims are little Zero-Dur balls. And so the idea is that everything will respond to thermal changes in the same way. And so in a relative sense, nothing moves with respect to each other. Okay, so now we've brought the photons onto the optics, and our CCDs are on the backs of these cameras. And so now we're able to take images of our exposed spectra. So this, for example, is what the HPF raw data looks like. You'll see these data are not very simple. There's a lot going on here. And so analyzing this data is not something you can do sitting down in an afternoon or something. And so these instruments come with very sophisticated pipelines that we also put a lot of effort into. So here what you're seeing in the HPF data is that there's all these different Echelle orders, and so you read this sort of like a book. It goes from red to blue, from left to right, and then top to bottom as well. And if I zoom in, you will see there's 3 fibers that HPF has. One is the star fiber, which here looks like mostly continuum. Then there's a sky fiber to keep an eye on what the sky is doing. And then all of these very precise measurements require having a simultaneous wavelength reference. And so in this case, we are moving to the future of wavelength references, which is a laser comb, which provides this beautiful picket fence of very homogeneous lines across your full band pass. And so you start with this raw data, but now you need to measure the radial velocity of the star. And so we have these complicated pathways of corrections that still need to be made, because if you just measure this data, the only corrections you're seeing are the hardware efforts. There's still all of the software effort to be made. And so here is my schematic for the Keck Planet Finder pipeline, which sort of takes all of the other pipelines I've worked on and brings together sort of the state of the art in algorithmic techniques. And this might be a little hard to read, but the point here is that there's a lot going on. This little box here encapsulates all of the processing that happens in sort of traditional spectrographs. So things like bias subtraction, flat fielding, and then extraction of the spectra. But getting to 10 centimeters means doing all of this extra stuff as well. So wavelength calibration that tries to figure out exactly where the rest frame of the instrument is at the time of observation underneath the science fiber. There's chromatic barycentric correction. So of course, if you don't correct for the motion of the Earth, the only planet you detect is the Earth. And so people have been doing barycentric correction for a while, but what we realized is that now you need to do it in wavelength space. So photons of different colors arrive at the instrument at different times, and so you can imagine the middle blue photon arrived at a different time than the middle red photon, and you actually need to know that difference because it matters at the 10 centimeter per second level. And so we have chromatic exposure meters that give us the mid times of all the colors, and then you can do a chromatic barycentric correction. There's also sky correction, so this is something that hasn't been done yet. Sort of what is crudely done is to just subtract the sky fiber to get rid of emission lines. But proper telluric correction, including microtelluric correction, which is tellurics that are smaller than 1% in amplitude, is going to be required basically to get to 10 centimeters per second. And then finally you get your radial velocities, but there is this other scary red box, which is stellar activity. So right now we're committing to measuring as many stellar activity metrics as we can, but correcting for it is really a whole field of research in exoplanets and in stellar physics. So as a little example, here's sort of how we're thinking of doing a new level of sky correction. So this is a paper I've been working on that actually submitted this morning. The idea here is that we've thought about telluric absorption and telluric emission usually, but there's a third contributor from the sky, which is a spectrum of the sun. So there's a faint spectrum of the sun that's floating around and is usually superimposed on your target spectrum, and it comes from moonlight but also scattered sunlight just in the sky. And so what happens is that you have a nice target spectrum, but then there's a low level G dwarf spectrum superimposed on top of it. This is an exaggerated cartoon just so you can see it. So here the effect is at the 10% level. But this superimposed contaminating spectrum is actually moving with respect to your target spectrum over time as the Earth goes around the sun. So this is determined by the barycentric velocity, while the target itself is potentially also moving because of the presence of a planet. And so there's relative motion between these, which means there's not only contamination, but it's time variable contamination, which is sort of catastrophic to these measurements that you're trying to make. And so what happens is that when you basically construct a cross correlation function and you measure the peak to try and get your radial velocity, that contaminating spectrum adds these extra little bumps to your cross correlation function that pulls on your fit when you're trying to get the peak. And that bump is moving around over time. And so that basically can cause variations in the radial velocity that have nothing to do with the presence of the planet. It's just from the moon and the sky and the Earth going around the sun. And so this is an effect that so far has sort of flown below the error budget level, and we haven't had to care about it at the meter per second level. But as we get into 10 centimeters per second, you have to correct for this. So from the hardware side, we've prepared for this by building in the sky fiber. But on the software side, we still have to show that we can use the sky fiber well enough to correct this out. And so here's some simulations I did to show how big is this effect? Do you need to really worry about it at the 10 centimeter per second level? And so here's sky brightness at Kitt Peak. Typical sky brightness is, gets as dark as about 22 magnitudes per arc second, but if you're looking towards Tucson, it gets kind of bright. And here's a range of stellar Vmags that NUID will typically look at. And so if you get really unlucky and things line up in a particularly bad way, this is the worst case that you could get. And so you can see that at the highest levels, the errors are in the range of like a few to 100 meters per second. And this is not to really say this is how bad the error is, this is the worst case, but we need to be able to correct the worst case so that we can observe in all conditions. And so this paper I submitted sort of walks through how we would use the sky fiber. And if you were able to get all of the information out of the sky fiber and use it pretty optimally, you could actually do a really good job. So the residual error here after correction for the brighter stars is at about a centimeter per second. And then all the way to the rest of the stars is about 10 centimeters. So that's good because we're beating this down by a lot. But if you're trying to find a planet that has a 10 centimeter per second amplitude, this is still a problem. And so you can't ignore the fact that most exoplanet observations are done in bright time. And so you really have to pay attention to where the moon is, how bright it is, and also how much shifted this solar spectrum is with respect to your target. So these are all of the things that we're doing to get better at finding smaller planets. But the payoff is sort of happening right now. A lot of these instruments are going on sky right now. Some of them have been on sky for some years, and we're learning a lot from them. And all of those lessons are sort of being transferred to the future instruments as well. and I'll show you a few highlights of the instruments I've been working on that are on sky. So the Habitable Zone Planet Finder was delivered to the Hobby Eberly telescope a little over a year ago. And I'll show you snippets of this video of what it means to build this really heavy, stable spectrograph and then transport it across the country in a FedEx truck and have it delivered to you see the Hobby Eberly telescope in the background. FedEx actually has a very nice white glove service that will bring your instrument to the telescope. I'm gonna skip ahead here, but you're very gingerly delivering the spectrograph to the basement of the HET. The HET is particularly nice because of all of this access that you have. Other telescopes, you have to lift it into the basement, which is not great. And I'm showing you this because another instrument, NUID, which looks just like HPF, is actually being shipped in a couple of days to Kitt Peak. So this process is going to happen again for the same team in the next few weeks. But the Habitable Zone Planet Finder has been doing great. It is one of about 4 or 5 near-infrared precision instruments that are coming online, and I've been saying 10 centimeters per second a lot. That's the goal in the optical. For the near-infrared, everything is harder because the technology is a little bit more behind. So the frontier there has been 1 meter per second. And HPF actually is the first instrument to get really close to it. This is still very early data of Barnard star. And you can see we're at about 1.5 meters per second. These are the best near-infrared RVs ever. And there's still work to do on HPF, and so we're hoping we will get to 1 meter per second. So all of these innovations for HPF, including a custom laser comb, all of that environmental control, all of the new data reduction techniques, etc., are actually paying off on sky right now. And I think there are plenty of people in this room who are using HPF as well. So this next generation of instruments is actually living up to a lot of its potential. And so NUID, as I mentioned, is actually shipping in a couple of days. We just had this major pre-ship review with a NASA panel, which we passed with pretty flying colors. But it was nice because even though we're still in the lab, we have a little solar feed. You have to be careful not to call it a telescope because you're not supposed to put more telescopes on these summits. But we have a little solar feed that has been looking at the sun while we're in the lab. And so this is some very early analysis I did for NUID looking at the sun. So here is the sun actually while we were doing the observations. You can see it's very quiet. There's no spots really on it. And these are the RVs of NUID looking at the sun over about 6 hours. So we're at about 38 centimeters per second. There's a lot of caveats to this result, including the fact that the wind telescope is not part of this system. But this is very promising as we go to the telescope. So we do all this work to have these really exquisite spectra where the PSF is very stable and the line shape variations that you see can now be interpreted as real physical phenomena, so either from the star or the planet. And so apart from just detecting the radial velocities of the stars as probes of planetary existence, there's a lot more you can do with these spectrographs. So one thing I'm really excited to do is to extend the procedures that we perform for the star onto the planet. So this is sort of the animations I've been showing you where the star wobbles because of the existence of the planet and the stellar spectra go back and forth. But really, if your planet is reflective enough, there's starlight bouncing off the planet that you are receiving as well. And so superimposed on top of your stellar spectra is a very, very faint reflected light spectrum from the planet. And this reflected light spectrum mostly looks like the star, but is modulated by the albedo of the planet and might be picking up some atmospheric signatures from it as well. The problem is that the planet is about 1 billion to 10 billion times fainter than your star. So this is sort of been prohibitively difficult till now, but with these new upcoming next generation instruments, this is something we are starting to consider. And so first of all, you need a lot of photons. So NUID should be able to do this for very bright planets, but instruments like the Keck Planet Finder should be able to do this even better, and then prepare this field of reflected light studies for the TMT and future instruments like HABEX and LUVOIR that will actually try to take pictures of these Earth-sized planets. And you also need all of these other properties. You need high resolution so that you can separate the star from the planet. You need stable spectra so that if you see tiny changes in the stellar spectra, you know it's from the planet and not from just your instrument. But also you need new algorithmic techniques. So this is stuff we're proposing to do on NUID as soon as it's delivered to try and prepare these techniques for the future. And I will end with a symmetric animation of the future of exoplanet detection. So we're where we left off in the beginning, and this is very optimistic, but I think optimism is warranted in the field. And so if instruments like Gaia, all of these ground-based spectrographs, TESS, and then in the future JWST, etc., live up to all of their potential, there's a lot of planets coming. And so 100,000 planets that will open up the fields of planetary evolution and studies of planetary atmospheres, and really hold a lot of payoff for all of this hard work we're doing now to build the next generation of instruments. And thank you for listening. With that, I'll take questions.
Thanks a lot for this very nice talk. Questions from the audience? What did you want to know about instrumentation?
This is a great talk, and it's all really exciting work. I just want to have some context about what the effects of driving our precision down to centimeter per second levels will actually do for the types of planets we might be able to find, like what size terrestrial planets, the effects on atmosphere that you were just talking about, actually getting atmosphere of the planets, stuff like that.
Yeah, so the 10 centimeters, of course, is set again by the Earth itself on the sun, which is actually more like 8 point something. But so to get to Earth mass, Earth radius planets, that's basically the few centimeter per second level that we're trying to get to. There is also some drive to get even lower than 10 centimeters, but that might be technologically sort of limiting, but there's some, kind of out there ideas of maybe flying some of these kinds of instruments in space, and so you get over all of the contribution of the Earth's atmosphere, which takes out a whole box of that error budget. In terms of studying atmospheres, so these instruments are really focused on stability and precision. But the side effect of that is that you can study line shape variability really carefully. You're still high resolution, so you're sort of photon limited all the time for single lines. But if you're looking at an ensemble of lines, say for a certain type of stellar activity that's manifested in a family of lines, becomes really powerful. And so reflected light is nice because it looks, the spectrum of it is just like the spectrum of the sun, and so the techniques that you're using to look at the sun or the star work directly on that. But you could do the same thing with, instead of cross-correlating with the stellar spectrum, you cross-correlate with what you think might be in the atmosphere of the planet. And this has been done in the near infrared, where younger, hotter planets are brighter. It's harder for rocky planets in reflected light, but it should be a technique that can be extended. And I didn't mention this, but the nice thing about doing direct detection in this spectroscopic way is that you're not trying to separate the planet and the star spatially. You're trying to separate them in velocity, which is naturally happening because the planet is small and has a larger throw-in velocity. And so you don't need the planet to be transiting. You can do this for all the planets, basically.
Hi. So near the beginning of your talk, you were talking about like how 10 centimeters per second, you're sort of almost limited by the size of atoms.
Mm-hmm.
So like, does that mean that there's a point where you literally will not be able to get below a certain velocity, or is there people thinking of ways around that barrier as well?
Yeah. So the way we get around it right now, because it's already very, very difficult right now. The way we do it is that if you had a single line moving that much, you would have no chance at all of detecting it. It's because you have thousands of lines from the star that you're watching. And so that means you're actually spread out across many more silicon atoms in a literal way. But we are sort of probably getting to the bottom of what this technique of looking for radial velocity signatures can do, because so far it's really been taking traditional spectrographs and then pushing them to the limit. But there are people thinking of innovative new ways of doing this. For example, do you really need to look at all of wavelength space, or could you look at certain lines, especially if you're trying to look for habitable planets in particular? And then you can move away from these huge mammoth spectrographs into smaller, more focused spectrographs. There's also been a push for moving totally out of wavelength space into frequency space, because a lot of these movements are more organically understood in like a frequency-based domain. So yeah, people are thinking of getting to a new level of precision beyond this, but it's probably not going to be using the same designs.
So in the graphic with the air budgets, it seemed like a big component was the atmosphere dispersions that we just alluded to. And so I was wondering how important it is to have an AO system associated, like on a telescope, dispersion plans for.
Yeah, so there's two or three new instruments coming up that are trying to do that, where they're behind AO. So Parvi is one. Then there's another one called iLocator that's going on the LBT. It helps to be behind AO because you have less sky in your fiber. The problem with those instruments has been basically getting enough light into the fiber, because fibers are tiny. Our fibers here are like, I don't know, about a few hundred microns. Those are a few microns. And so right now they're still stuck at, 20-30% light into the fiber, which makes it impossible to do the rest of the get the light all the way through to the detector. And so, but once they get better at that, that is very promising. And like I was saying, if we were to fly this technology, it would have to be something like that, because it would be small, meant for AO, it would be in space. And so, yeah, that's kind of the parallel path forward that's also being explored.
We would have time for one last question. I was actually wondering, so for all those corrections you need to do, what is kind of the timeline? How long does it take after, like, you acknowledge there's like this big problem, and then, like, in terms of PhD thesis?
Yeah, that's a really good question. So, yeah, I'd say like one PhD thesis is equal to solving like 2 or 3 of those problems, and some of those are big enough that they're one whole PhD thesis. Like the problem of tellurics is really hard, because you have to like understand the Earth's atmosphere at a level we don't, and so you also have to maybe have some PhDs in atmospheric science that go with the astronomy ones. Yeah.
Thank you.
Mm-hmm.
And with that, let's thank Arpita and also Kirk again.
Thanks.